whatever we have studied so far in this unit can be said to be a part of only the subject electronic devices and circuit. But what we are going to study from now will be constructing the basics of not only the electronic devices and circuit but also of analog electronics. In masters or even in the last chapters of standard graduate level textbooks, you may not be able to correlate the two subjects, but when we talk about the basics, then you may think that you are reading the same things again. However, as a general interpretation in electronic devices and circuits, you will learn in great depth about what is an electronic component and very limited use of these components in the circuit. However, in analog electronics, the opposite is true. You do not study in much depth about what is a component, how these are constructed, but you analyze how these electronic components are used in design circuits which will provide us the desired input-output relationship. You will use terms like power amplifier, oscillator, op-amp, current mirror, but do we grow these on plants? Of course not. There is no such plant, neither they are just laying around above the earth crust. We construct them with the help of components like diode, BJT, MOSFET, JFET, etc. You are learning about diodes in this unit, and in the later units we will study about BJT and MOSFET. These are the components which helps in designing amplifiers with desired properties. You may not know much about power amplifier, oscillator, current mirrors, but you must have already studied about basic logic gates like OR gate, AND gate and NAND gate. So, do these grow on trees? Again no. These are also constructed with the help of diodes, BJT and MOSFETs. So you see that the subjects are quite interlinked. You are studying about components here and few basics about how to use them in circuits. But eventually you will study more complicated use of the same components in other subjects. So I only request you to pay more attention, as things which you will study from now will be linked to other subjects directly. I hope you are very clear about what is contact potential or built-in potential V0. Now we are going to draw energy band diagram of a PN junction. First, as usual, we will draw the Fermi energy level. Now we will divide the region into three parts: P-type region, depletion region and N-type region. You know that in the P-type region, Fermi energy level is closer to the valence band energy level. Similarly, in the N-type region, Fermi energy level is closer to conduction band energy level. We have to make sure that the energy band gap in the P-type and N-type region is equal, because we are taking the same semiconductor material. After we are done with the P-type and N-type, we have to join conduction band and valence band of the N-type and P-type region. And the difference in the energy gap is equal to Q, which is the charge on a charge carrier, multiplied by built-in potential V0. Remember that the point which is lower in the energy band diagram is at higher potential. Therefore, conduction band energy level in the N-type region minus conduction band energy level in the P-type region is equal to Q into V0. Same can be said for intrinsic Fermi energy level and valence band energy level. But this is the energy band diagram of a simple PN junction without any external battery connected to it. Now let us connect an external battery. In the circuits, diode will never be represented like this, as you already know that PN junction or diode is having a symbol. Therefore, by replacing the PN junction by its symbolic form, we can represent this circuit like this. Obviously, battery will be having some potential drop and will make one side of the junction more positive with respect to other, and this is referred as biasing. Even though the world is fighting for unbiased treatment for all races and gender, but battery is quite biased. It won't give same potential to both sides, as it won't be of any practical use then. Now, we can have three cases: whether the applied potential is negative, or it can be zero, or it can be positive. Forward bias is said to be done when the P side is connected with the positive terminal and the N side is connected to the negative side. Reverse biasing is opposite of that. As you can see from the energy band diagrams of reverse bias and forward biased, that the depletion width is also dependent upon the applied voltage. If we apply a negative voltage, then the depletion width increases, whereas if we apply a positive voltage, then the depletion width decreases. As a matter of fact, after a certain positive voltage, this depletion width completely disappears. It is quite interesting that in forward biasing, battery voltage actually opposes the built-in potential, and as forward bias voltage is increased, depletion layer width reduces as energy bands on the N side are raised. When the forward bias voltage is equal to built-in potential, the depletion layer completely vanishes as the energy band will get aligned and the majority carriers can cross the junction.